Good afternoon and welcome to my laboratory. Uh, Due to the present controversy over the Ainslie Paper 1 Figure 3 scope trace, I've decided to resurrect Tar Baby and do another demonstration of just exactly what's going on here. Okay, so first, here's Tar Baby in its travel box. This is the circuit board. All of this stuff from here to the left is an independent 555 timer and charge pump inverter that allows the main circuit to be run off of the run batteries only with no extra battery or function generator. But we're not using that right now. What I'm doing right now is running the thing in the very strict, straight Ainslie mode with the function generator, this red lead and this black lead here, F43, providing a signal to the MOSFETs. Excuse me. And right now we're providing that signal at 1.5 kilohertz. And it's a little rectangle wave. I've got the amplitude turned down right now. We're looking at this A channel, which is coming from the function generator directly. So that's the gate drive signal, what is usually the blue trace on Ainslie's scope traces. That's identically that. And we're looking at this right now at 5 volts per division, and the center baseline is that gradical marker right there. So we're seeing a symmetrical pulse that goes over and below the baseline, positive and negative, and we're 5 volts per division on the gradical line there. The B channel up here is the current viewing resistor in the normal position, and in the Ainslie scope traces that's indicated by a golden yellow trace. Okay. So I only have a 2-channel oscilloscope, so those are the only traces that I can show simultaneously. We are triggering the oscilloscope off of the function generator's sync output to the external trigger input of the HP180A oscilloscope, and we will be looking at the B trace at 0.2 of a volt per division using an attenuated probe, 10x attenuated probe. And since the current viewing resistor that I'm using is a 0.3 of an ohm, 0.3 ohm current viewing resistor, so it'll be very close to the value that Ainslie is using of 0.25 ohms. 0.3 ohm current viewing resistor. Okay. And we have the 4 Q2 MOSFETs on their individual heat sinks over there, and a Q1 MOSFET here. These are all IRF PG50 MOSFETs, and they are connected with about the same length of wires that Ainslie uses to connect her MOSFETs to the main board. Then over here I have an oil bath load that corresponds to the inductance and resistance of Ainslie's load, and I'm monitoring the temperature of that load with a little analog thermometer, and right now it says 81 degrees Fahrenheit. Okay, so that's the load. And over here I've got the 2 batteries. We're just running with 24 volts right now, and I've got that disconnected. This is an inline current meter just to tell me when I'm drawing current. Here I have the Fluke 83 multimeter with its temperature adapter monitoring a thermocouple that is attached to the Q1 MOSFET. So we're monitoring the temperature of the Q1 MOSFET, and that's in degrees centigrade right there. So we're looking at 23 degrees, 24, 23 degrees centigrade on that MOSFET right now. And then this over here is my MOSFET test board that allows me to verify that MOSFETs are in fact working properly, very simply by using them to control the brightness, of a little 12-volt automotive bulb in a very, very simple circuit. Okay, so that's the whole setup to examine the issue of the mystery scope traces. Okay, so the first thing that I'm going to do here is illustrate something very important. I do not have the battery hooked up. Now this is exactly the Ainslie circuit that is described in paper 1 with the scope probe positions exactly as given in the Ainslie circuit. Okay, figure 1, paper 1. Alright, now remember that the B trace here is monitoring the current through the current viewing resistor. The A trace is monitoring the gate signal. This is the blue trace, this is the golden yellow trace. Now as I turn up the amplitude of the function generator, look what happens. A couple of things happen. Okay, first of all, because of the diodes and the MOSFETs, the amplitude of the function generator's output can't go over about plus or minus 4 volts. No matter how high I turn up this function generator output, there it's maximally up, but the signal output is still only about 4 volts. But look what happens to the current through the current viewing resistor. I get buku current through that current viewing resistor without any battery supply hooked up. This is coming from the function generator, people. The function generator is acting as a power source, people, and contributing to the current through the system. Okay, and I'm going to turn this back down. Alright, and we'll apply some power here. Okay, so go ahead and hook up the 24 volts power to the circuit, and now I'm going to increase some amplitude here. Oh, by the way, we're not using any offset on the function generator yet. So I'm going to increase the amplitude, and now you see something going on here. This is current through the Q1 MOSFET. Remember, now we're giving the Q1 MOSFET a positive gate signal, and it's coming up. It came up higher now. It's up to 5 volts, and when that happens, the Q1 MOSFET turns on. Right? We haven't started seeing any oscillations yet because we don't have enough negative voltage yet. So let's add a little bit of negative offset. We put the negative offset on and then lower it a little bit. You don't see it going down here because remember it's clipping at minus 4 volts. But the more negative offset I apply, the more current we're actually putting into that clipping there, and that's what causes the oscillations. Whatever the part of the circuit is that's causing the negative voltage supply to the system from the function generator not go below 4 volts negative, appear to. That's injecting current into the system, negative bias current, and that's what's causing the oscillations in the Q2s. Okay, but remember the Q1s are turning on during this upward portion here, or they should be. So look at what's happening in between those guys there. Okay, as I increase the amplitude of the function generator positive drive and add a little bit more negative offset, where are we here? Like that. Okay, I start getting strong turning on in the Q1. Okay, and the oscillations when the Q1 is off. All right. And in that situation, the digital thermometer kind of goes crazy. It reads something incorrect because of the oscillations. Okay, so I'm going to turn the oscillations off, and then we can take a reading of the digital thermometer that's accurate and not disturbed by the RF pickup. 26 degrees centigrade. And so this MOSFET has warmed up a little bit from just the current that we were putting through it just then. Okay, now here's the trick. Okay, if I go back up here and get some oscillations and enough current in there to actually get some current showing on the system, right? and then I remove the Q1 MOSFET just by unplugging it. I just completely unplugged it, right? Now you get a trace that looks like the figure 3 trace that Ainslie has been publishing. You get enough drive from the gate drive, but you get essentially no current flowing during the Q1 off, or rather the Q1 periods when it should be on. Okay. Now I'm going to plug the Q1 transistor back in, like that. And this is what you should be seeing when you have a functioning Q1 in there. I've exaggerated it a little bit. Ainslie's drive is actually only going to give you this kind of a jump up there, showing current flowing. But it's easy to get a little bit more or a little bit less, but here now the Q1s are not getting enough to turn on, and it's easy to see that that's the case because you only have a plus 3 volts here. But Ainslie is showing a plus 10 volts or so drive to the Q1 transistors, so they should be turning on very, very strongly like that, unless, of course, they're missing or unplugged or open from failure. Okay, and once again we've warmed up just a little bit from doing that. Alright, now let's take this Q1 MOSFET and test it to make sure that it's actually working properly. So I take it over to my test bed here and I just stick it in the socket, and then make sure we're giving it 12 volts, and then we crank the knob until we get a light, and then we look very, very small crankings of the knob to make sure that the MOSFET is still operating in the linear conductance region, or can operate like that. Okay, so we've just tested this MOSFET for shorts, opens, and proper response to a gate drive signal, all in what, 10 seconds or so, right? All right, that's it. Thank you for watching.